Earthquakes in subduction zones. They are a significant hazard for millions of people around the globe. To understand this hazard, we need to know what causes an earthquake. Simply speaking, earthquakes nucleate when stress builds up and reach the strength of the rock. During the earthquake, the stress is then released and the earth moves, slip and seismic waves. But what causes this buildup of stress? And where do we expect it? For that, we need to take a look at the temperature. Megathrust seismicity is responsible for some of the largest events in the world. Think of the 2011 Tohoku earthquake in Japan, or the 2004 Sumatra Boxing Day earthquake. This type of seismicity is limited by the downdip limit of the seismogenic zone, which in turn is determined by the transition from brittle deformation to ductile deformation. And what causes this change in deformation mechanism? Temperature. Intermediate depth earthquakes occur at depths of 75 to 300 kilometers. The mechanism thought to be responsible for these types of earthquakes are dehydration reactions. The depth at which these dehydration reactions occur is determined by pressure and, you guessed it, temperature. So, in order to understand seismicity in subduction zones, it might be a good idea to look at its thermal structure. Of course, many studies have already investigated this, and they've helped us gain insight on the relation between temperature and seismicity. However, amongst others, they make one simplification. In the equations, they use constant values for the thermal parameters: thermal conductivity, heat capacity, and density. Lab experiments show that these thermal parameters actually depend on temperature. So does it matter that models make these simplifications? Does the thermal structure change when you use temperature-dependent parameters? That is what I investigated and will show you in this video. What is the effect of using temperature-dependent thermal parameters in thermal models of subduction zone? To investigate this, we use a simple model based on the subduction community benchmark presented by Van Keken and others in 2008. We have an oceanic plate that dips below a stationary overriding plate at 45 degrees with a velocity of 5 centimeters per year. To describe the initial temperature of the subducting slab, we prescribe a plate model as the left temperature boundary condition for a plate age of 50 million years. We deliberately choose such a simple setup so that we can isolate the effect we are interested in: temperature-dependent thermal parameters. So how do the parameters change with temperature? Let's have a look at the functions derived from data. For the thermal conductivity, we use two possible functions: Hofmeister 1999 in pink and Xu et al. 2004 in blue. The constant values used by the Van Keken benchmark are indicated in orange. As you can see, the thermal conductivity varies quite a bit with temperature. The same is true for heat capacity. Many different functions are possible to describe its temperature dependence. I still prefer the pink one. Lastly, density. A change from 3,325 to 2,975 kilograms per cubic meter, depending on the temperature. For reference, we first ran a model with the constant values by Van Keken and others in 2008. This is what that looks like. If instead we use all the pink functions for temperature dependence, the model looks like this. Time for a game of spot the differences. No, we really don't have time for that. Oh, okay. I guess I'll just plot the differences then. Look at that color bar. Quite a big difference in temperatures, right? Well, we are only interested in the slab at the moment, so let's focus on that, adjust the color scale, and block out the mantle wedge. When we use temperature-dependent thermal parameters, the top of the slab is colder and the bottom of the slab is warmer. And within the slab, the temperatures can change by up to 65 degrees Celsius. We can also look at the maximum depths our temperatures or isotherms reach within all the models we used in this study. Here we have our reference model, the effect of different temperature-dependent functions for the thermal conductivity, different functions for the heat capacity, and the density. In the all model, we combine the preferred pink temperature-dependent functions of all three parameters. The downdip limit of the seismogenic zone is typically defined by the 350 to 450 degrees Celsius isotherm. So if the depth of this isotherm changes, the size of your seismogenic zone will change. For example, when you include temperature-dependent thermal conductivity, your seismogenic zone becomes larger, and that means bigger earthquake. On the other hand, for temperature-dependent heat capacity, the seismogenic zone decreases. Smaller earthquake. These opposite effects do not completely cancel each other out, as the all model presented here shows a larger seismogenic zone. Bigger earthquake. The 600 degrees Celsius isotherm is associated with dehydration reactions, which in turn could be responsible for the intermediate depth seismicity. Here we see that the depth at which your model would predict intermediate depth seismicity to occur changes dramatically with your choice of thermal parameters. So, conclusions. Next time you are using thermal or thermomechanical models of subduction, consider using temperature-dependent thermal parameters instead of constant values, because it really does change where you would expect your seismicity to occur and how big the biggest earthquake could be. Hello! I tried yet another style of video. Let me know if you liked it by liking the video or not. If you disliked it, don't click dislike, please. And while you're at it, maybe subscribe, because we do all kinds of fun things on this channel to do with academia, research, and earth sciences in general. Outreach, science communication, support the cause. Thanks so much for watching my EGU presentation, and I hope that we can actually meet again in Vienna sometime soon. Bye!